All right, folks. For 3.1, we're going to be talking about um, association between two quantitative variables. So how do we describe association? How do we plot that association, etc.? So there's a few objectives in this first section. We want to be able to identify explanatory and response variables. So those are two big vocab terms. In situations where one variable helps to explain or influence the other, we will make scatter plots to display the relationship between those quantitative variables, describe direction, form, and strength of a relationship displayed in a scatter plot, and we will interpret correlation. Understand the basic properties of correlation, including how it's influenced by outliers, and then we'll use technology to calculate it. Finally, explain why association does not necessarily imply causation. So a couple important terms to get down. We're going to be moving from here into statistical studies. So this is kind of the beginning of that vocabulary. A response variable is measuring an outcome of a study, and the explanatory variable may help explain or influence changes in a response variable. So generally, we put the explanatory variable on the x-axis, right? When you're in algebra, we call this the independent variable. We put the response variable on the y-axis. This doesn't mean, just because you have an explanatory variable and a response variable, it doesn't mean that the explanatory is causing changes in the response variable necessarily. And we'll talk in the next unit about how to determine a causal relationship. But right now, all we're looking at is there is some possible association between those two variables. So scatter plots, you've probably made these before, and it shows the relationship between two quantitative variables measured on the same individuals. So the values of one variable will appear on the horizontal axis, and the values of the other appear on the vertical axis. As I said, you generally want to put the explanatory variable on the x and the response on the y. Label and scale your axes, and then we'll plot data values. When you make scatter plots, we will largely do them in the calculator, and then if it's on a test, you would just copy it from your calculator to the paper using sort of the same way we did with like histograms. So you want to make sure you scale your axes. You want to make sure that you label what your axes are as well. All right, so I will go ahead and show you how to make a scatter plot in your calculator. So the table below shows data for 12 students in a statistics class. Each member of the class ran a 40-yard sprint, then did a long jump with a running start. We want to make a scatter plot of the relationship between sprint time and long jump in inches. So I would say here that the relationship that they are implying is that sprint time helps us to predict long jump, meaning a faster sprint time would get you a further long jump, which would make the sprint time the explanatory variable and the long jump the response. So this is the explanatory, this is the response. All right, so let's grab our calculators. What we want to do then is pull up a table. So we'll go stat edit. If you already have data in there, just clear it out. I'm going to put my sprint times in list 1 rather, and I'm going to put my long jump distances in list 2. So I'll go back. You can pause it here and just get the sprint times in list 1 and the long jump in list 2. Okay, so I have my data entered. One thing I want to mention is just make sure that when you enter it, you've entered list 1 and list 2 in the correct order, since these are measurements on the same individual. All right, so once we've done that, one thing I need to do is just go in to y equals, and if there's anything in there, I want that turned off. So now I'll go second y equals. I'm going to go into my stat plots. I'm going to turn plot 1 on. We're going to highlight the one that looks like a scatter plot and choose that. I do want my X list to be from list 1 and my Y list to be from list 2. If you need to change up those lists, there are shortcuts on your keypad. If you hit second and one of these, you can see above 1 you have list 1, then list 2, list 3, 4, 5, and 6. All right, now we can go ahead and quit out to the main screen. I'm going to go to Zoom, and we're going to choose Zoom Stacked. So this will give us a good window that will fit all of our data within it. And there we go. All right, so to be able to copy this down to your paper, you really just want to copy the rough form and then, again, give some sense of scale on the X and Y axis and label what they represent. So you can hit trace and use the arrows and it'll jump around from point to point to give you some sense of scale. My recommendation is minimum you want to find kind of the furthest to the right and the furthest to the left so that you can sort of give some sense of scale on the XY axis. So I went ahead and copied this down to my notes there. And so I just copied the general pattern and I labeled a few of the points to give some sense of scale on the X and the Y axis. And then I also labeled what the axes were and what units they had. Okay, moving on. So how do we describe a scatter plot? It's the same kind of idea as when we were describing a distribution of a single variable. We had that acronym SOX, right? And that was shape, center, spread, and outliers if there are any. And you also need to provide context. So the acronym here is DOFS, and it stands for direction, outliers, form, and strength. So direction meaning, is it a positive or negative association? So going up towards the right would be a positive association, down towards the left would be negative. Sorry, down towards the right would be negative. Form is it linear roughly, or is there a curve to it? And then strength is how closely does it follow its form? Are the points tightly packed together in that form, or are they loosely spread apart? And so when you discuss strength, it's going to be basically a continuum between weak association and strong association. And then an outlier is just right now any individual that falls outside the overall pattern of the relationship. And all you would need to do is just discuss that there is one there and make a note of it. So for the last example, I might say the relationship between sprint time and long jump distance is a moderately strong negative association that looks roughly linear, right? There's a clear downward trend here. I don't see any curvature, and then I don't see any outliers. So just make sure when you begin a discussion of this, you add context, which means just talk about the data in terms of the units that are provided. So, like I said, two variables have a positive association when above average values of one tend to accompany above average values of the other. and when below average values also tend to occur together, and then they have a negative association when the opposite is true. So above average values of one tend to accompany below average values of another. All right, so let's do an example here. McDonald's restaurants offer a variety of salads. So here we're given the sodium content versus the fat content of each salad. And we're going to make a scatter plot of that relationship. And then we'll describe that association. So for these purposes, it's not 100% clear, but let's just assume that the sodium is the explanatory and the fat is the response variable. So we put sodium in X and fat in Y. You're just going to want to go to your calculator. We're going to go back to stat edit. Let's clear out list 1 and list 2. Let's put our sodium content in list 1 and our fat content in list 2. So you can go ahead and pause it here, get those values entered. Okay, so I've got my sodium in list 1, my fat in list 2. Just a reminder, you're going to go into stat plot, make sure that's turned on. Got a scatter plot selected. My X list is list 1, my Y list is list 2. I'm going to go zoom, choose the 9th option. There we go. And then we want to copy this onto our notes. Okay, so I said there is a moderately strong positive linear relationship between sodium and fat in McDonald's salads. The salads are comprised of 3 main groupings that seem to associate with chicken preparation, and the side salad is a possible outlier. And so I'm talking about these 3 main groups here. And if you look at the numbers and compare it with the information they give us in that table, it does seem like the crispy chicken has higher sodium and fat content, whereas the grilled preparation of chicken has more moderate sodium content and fat content. And then the side salad is just a weird one. There's no chicken in it, so there's much less fat and sodium for that. So just making sure you're hitting those key categories: direction, form, strength. If there are any outliers, talk about those. And then make sure you're doing it in context, not just talking about abstract numbers. All right, so how do we measure how linear an association is? That is what correlation is. This is an often misused word. People will use it when what they mean is association. But correlation specifically tells us how linear, how strong the linear relationship is between 2 quantitative variables. And so it's a number, and here are some of its characteristics. R is always a number between negative and positive 1. If R is greater than 0, that indicates a positive association. If it's less than 0, that indicates a negative association. The closer the values are to 0, the weaker the linearity of that relationship, meaning kind of the more random scatter you would have. So the strength of the linear relationship increases as R goes away from 0 and towards negative or positive 1. The extreme values of R equals negative and positive 1, only it happens in the case of a perfect linear relationship. So like that would be a situation where R is negative 1. That's a situation where R equals positive 1. Perfect linear associations. The more random the scatter is, the closer you'll get to 0. All right, so here are just a couple of examples. It's really hard to get a correlation of R equals 0. But here you get a general idea of just some other examples. Correlation of negative 0.3, so there is some correlation, but I would refer to this as weak negative. So R equals 0.5, you're starting to see more of the pattern in that one. So now we're getting towards moderate. Negative 0.7 I would call moderate negative. And then both of these are strong. So this one I would call strong positive, strong negative. Okay, so this value, this correlation coefficient, is also referred to as Pearson's coefficient, named after the guy who came up with the computation to get that value. And these are just rough rules of thumb. You can kind of intermix these words, but just to give you some sort of idea of how to describe the strength of correlation based on your R value. So anything between 0.2 and 0.5 is weak. 0.5 to 0.8 you could probably discuss as moderate, and then 0.8 to 0.1 strong. And you can kind of intermix some of those words for in-between values. So you've heard me describe associations as moderately strong or moderately weak. In here would be very weak or no correlation. All right, here is the formula to compute that R value by hand. So the values of the individual data are x1, x2, and so on. And you can see what you're doing is basically computing a z-score, because we're subtracting the mean and dividing by the standard deviation for each individual piece of data for your explanatory variable. Then you're computing a z-score for each response individual, and you're multiplying those together. So for each data set, you're computing an x z-score and a y z-score for every individual, and then finding the product of those two associated individuals. And so you're adding up all those individual products, and then we're going to divide by the number of data we have minus 1. The good news is you're not going to need to know how to calculate this by hand. I just show it to you in case you are asked about what's going on. There could be a multiple choice question about how it's computed, and you should just understand that it is the product of the individual associated z-scores. You add up all those products and divide by number of data minus 1. But your calculator can find correlation for you real easily as long as you put that data into lists. All right, a couple more facts about correlation, then we'll do an example. How it behaves is much more important than the details of that formula, as I was saying. So it makes no distinction between explanatory and response variables, meaning if we were to switch our lists and recompute, the correlation would be the same, okay? R has no unit of measurement because it's z-scores. They're standardized scores, right? So no unit of measurement. To have a correlation, remember, it's a measure of how linear an association is between quantitative variables. So if somebody says something like color is correlated to your impulse to buy, that's why they always put red at the front of the stores. That makes no sense because color is not a quantitative variable. And that it doesn't make sense to say that a relationship between categorical variables are linear. So what they mean in that case is that color is associated with your impulse to buy something. That's why they always put red at the front of a store. So correlation requires that both variables be quantitative. It doesn't describe curved relationships. and it is not resistant. So R is going to be strongly affected by outlying observations, and we'll talk about the ways that that can happen. It's also not a good complete summary of two variable data. So just like we talked about with one variable data, you want to look at a graph, you want summary statistics as well, and you want a description of the relationship, okay? So we need all of those things. So correlation is just like a descriptive statistic of the relationship, but we would also want to plot the data on top of that. Okay. Let's talk about a few questions here. Which association is more linear, R equals 0.5 or one with R equals 0.9? First of all, I want to make a note. We would need to see the data. To get a good idea, because you can have some curved relationships that give you a large correlation. But if this is all we're given, R equals 0.9 has a stronger linear relationship. Is correlation a resistant measure of strength? No, which we just mentioned. All right, so in this example, we're given a scatter plot of the long jump distance, long jump data from earlier, and it tells us that the correlation is negative 0.84. Interpret the value of R in context. All right. So I would say there is a moderately strong negative linear association between sprint and long jump. And so, like I said, that correlation of negative 0.84 tells me that the relationship is negative. And then on that spectrum, so we're somewhere in this range, right? Right in the middle of strong and weak, which is why I used moderately strong. Now, in terms of what it's doing to what that red point is doing to the correlation, what you want to think about is if you were to draw a line of best fit, how does that point in particular, and right now we're just eyeballing the line of best fit, we'll have a much more mathematical way to come up with a line of best fit soon. Is that point close to that line or is it far away? So if it's close to that line, then it's strengthening the correlation. If it's far away from that line, then it's weakening the correlation. And I think that this point deviates a little bit from the rest of the pattern, so I think it's weakening the correlation. And so, I mean, making it closer to 0. But we can actually check this because this is the data that we have in our calculator right now. So let's bring the calculator back up. Oh no, we have the SALT. This isn't the same data. This is the McDonald's data. So I'll go back and enter this data. Okay, sorry. So I came back here and re-entered that data into my list. So just pause it here and re-enter it in your list as well. List 1 sprint, list 2 long jump, because I'm going to show you how to find correlation in your calculator. So pause it here if you need to. All right, so once you have that data entered, let's get that scatter plot back up. I'll just do a zoom 9. There we go. Now I want to use the trace tool. Let's find that single piece of data that they were talking about. So it is this one. It's the one at 7.25110. All right. Let's quit to the main screen, so second mode. Oh, one thing I need to have you guys do if you haven't yet, we need to turn diagnostics on. You only have to do this one time, so I'll show you how to do it. You're going to go to second catalog. This brings you to the catalog of all functions your calculator has in alphabetical order. And you can press a letter and it'll jump to that letter. So I want you to press the D, which is the X inverse button. We're going to scroll down until we get to a function that I'm looking for called diagnostic on. You'll hit enter. It'll bring that function to the main screen. You'll hit enter again and it'll just say done. You only need to do it that one time. All right, so now that that's done, we're going to go back to stat. We're going to do a calculation. We're going to do linear regression, linreg, and we'll talk about what that stands for in 3.2. Now, I want to tell it that my X list is list 1, which remember those shortcuts are on your keypad. My Y list is list 2, frequency list. You can just leave blank for now. Store regression equation, I'm not going to do that. Then I'm going to hit calculate. And the value that we're looking for is right here. That's our correlation, which we said was negative 0.84. And if you round it to do decimal places, that's what it is. So that's what my correlation is, moderately negative, moderately strong negative, right? Now, what I want to do is go back in and take that single point out. So I'm going to go back into stat edit. I'm looking for the point that's at 7.25. It's the last one, 110. And I'm just going to delete that point out of there. So my guess was that that single point was weakening the correlation. So if that's the case, then when I rerun that regression, go to stat calc, linreg, hit enter again. As you can see now, my correlation is about negative 0.87, so it's even stronger than it was before. So kind of my guess was correct. That point did weaken the correlation. All right. Student wonders if there is a relationship between foot length and height. She measures herself and 6 classmates and produces the following data. So use your calculator to find the correlation between height and foot length, and do the data show any evidence of a relationship between these two variables? Explain. So I want you to go ahead and take a second and try this one. We'll call this student example 1. Go ahead and decide which you think is the explanatory and which is the response variable. And see if you can use your calculator to find the correlation between those and answer the question, is there any evidence of a relationship between these two variables? Pause it here, get started on that. And then I have one more student example I'm going to walk you through, so don't just shut down your computer. All right, we will talk about the answers to these questions when we go over the student example. So how would R change if all the heights were reduced by 5 centimeters? And how would R change if the heights were measured in inches rather than centimeters? So there were 2.54 centimeters in an inch. And then answer this question for yourself. If another student with a foot length of 19 centimeters and a height of 167 centimeters were added to the data, how would that influence R? What I would suggest doing is adding that data point to your data sets and regraphing the scatter plot and look at where that point is with relation to the rest of them. Does it increase the strength of the correlation or does it decrease the strength of the correlation? Here's your last student example. It's a multiple choice AP exam question. So pause it here one more time. And again, we will go over this in the next class. That's all I got for you on 3.1. We'll talk about this next time.